Right, I guess we can get started. So welcome to the Real Data Science Meetup USA, which used to be the LA Data Science Meetup. So I'm the organizer. For those of you who never met me, my name is Szilard, and I have the pleasure of introducing myself as the speaker of this meetup. So a little bit about myself. Last century, I was doing physics and finance, and then for the last 20 years, I've been doing data science, mostly in California before I moved to Texas last summer. So I also started the R meetup in 2009, and this meetup a bit later. I've been teaching, and I've been doing machine learning, and I have these benchmarks that I'm also gonna touch a bit on that today. And of course, anything I say here has nothing to do with my employer. So we are all fans of deep learning, so why not start with deep learning? So this slide is probably more than 10 years old. It originated when deep learning became a hype, and the claim was that deep learning will beat every other algorithm. We just need more data. And of course, deep learning had a lot of success in computer vision, also in virtual environments such as games, where you can generate as much data as you want. And also the world is simpler than real life. And also deep learning had some success with natural language processing. However, we've been promised self-driving cars for many, many years, and I don't see real full self-driving cars coming anytime soon. And of course, a lot of people have been talking about AI, and that's even further from being realized in the next few years or maybe even decades. However, we've been having machine learning and applications in businesses for many, many years, at least 30 years, if not more. These are the posters for the KDD conference. And these business applications of machine learning have been in many industries: fraud detection, credit scoring, marketing analytics, manufacturing, insurance, telecom, and a lot of this kind of business areas. So the common denominator with all of these applications is that the data in these business applications is most often structured data of tabular form. So we have observations stored in rows, and then we have variables or features as columns. And this data is typically relational, is stored in a relational database. So what I've been asking myself a number of years ago is that can deep learning match or even beat the accuracy of this traditional machine learning algorithm or this kind of typical tabular structure of data sets? And I tried. I also contacted and worked together with some of the brightest minds in the industry who know much more about deep learning than myself, and also who developed some of the gradient boosting and also the deep learning implementations like Arno, and also Tianqi Chen, who you might know is the author of original author of xgboost. And we couldn't really tweak neural networks in such a way that we achieve the accuracy of gradient boosting or random forest. So my conclusion at the time was that for tabular data, which honestly makes up most of the data in businesses, at least the data that can be converted into a lot of money, gradient boosting usually beats neural networks and deep learning, no matter what the hype and no matter what we call deep learning or AI or whatever. A bit later on, Tianqi Chen has also looked at this, and he looked at, in 2016, this is a slide from the Meetup talk he gave in LA in 2016. He looked at the previous year of all the Kaggle competitions from the previous year, so which algorithm was used in the winning solution. And in about 2/3 of the competitions, the winning algorithm was xgboost, and in the other 1/3 it was deep learning. And it was kind of along the line that if it was tabular data, structured data, then it was mostly xgboost, and if it was images, speech, text, then it was typically neural net. Also talk a bit later from Anthony Goldblum, who is the CEO of Kaggle, was kind of along the same lines. And since then, many others have expressed the same feeling that, for example, here's Gilberto, who was for a while Kaggle's #1. He says, in my experience, the GBMs are by far the best for tabular structured data. Or more recently, Boyan, who also is a strong proponent of using xgboost for tabular data. So I asked on Twitter recently what people think are best for tabular data. Obviously, it's my followers, so it will be very biased. Same on LinkedIn. And I had the impression that most people by now know that if you have tabular data, then you should use gradient boosting. But then Boyan says that maybe this knowledge is not that mainstream. So perhaps this talk will be useful. So, by the way, if you've been doing machine learning for years, this fact should not be a surprise. So there is these 2 wonderful studies from 2006, which I always recommend. They are from overlapping authors, so a lot of commonality. They have looked at many data sets, many algorithms, and the ones that came on the top was random forest boosting and neural networks. So random forest came up at the very top because these data sets were at the time smaller, but for larger data sets, boosting usually beats random forest. I think someone is unmuted, so I'm gonna mute. So I've been using gradient boosting and random forest in R since around 2006, probably these versions when I started using them. But how about more recently? So there has been a lot of work in trying to make this kind of specialized methods from deep learning work with specialize them to work better with tabular data. And there are many of them. Some of them, they are based on encoding data, like think of embeddings. Some of them are specialized architectures. For example, very popular transformer-based models. And then also there are some of these methods, they use regularization. They think that neural networks don't perform very well on tabular data because they are not regularized enough. So there is a great paper that appeared in February. It's a survey of all these methods and how they perform on tabular data. So I highly recommend everyone to read. It's not very long, about 20 pages, I think. And here are the results. So they have compared all these methods and they also added gradient boosting and random forest and some of these other boring machine learning algorithms. So you see on the vertical axis, it's accuracy, so higher, better. And on the horizontal axis, you have training time. So you spend a lot of time training this very sophisticated deep learning specialized for tabular data algorithms or methods, and yet gradient boosting like xgboost or catboost still beats them in accuracy. So they haven't been able to reach the accuracy of gradient boosting on tabular data, even though these have been specifically developed in order to work well with tabular data. Yeah. So how about there are these papers? So each of these have papers introducing them and comparing them to other methods, sometimes to xgboost. And in some of those papers, it's claimed that their new method that they just came up with beats xgboost on some data set. So it turns out that some of those studies are completely flawed. For example, this one was a discovery of Rajiv Shah. The Sarkos data set has been used in several studies, and it turns out that the test set just contains a lot of examples from the training set. So all you do is just overfit the training set, and then it will show spuriously like wonderful performance. So whenever you see a new method, then be wary about if they claim that it beats everything else. Specifically to TabNet, there is also an open source implementation besides the original proprietary Google one. And I looked into it. So the results are on the same GitHub repo I'm going to mention later, the one I used to study the GBMs. And it turns out that it's not only not very accurate, but also very slow. So at least 10 times slower than xgboost, for example. And this was after tweaking it. So I had a lot of help on GitHub from the author of this package, the PyTorch TabNet. So it's been very helpful. And if you look at this GitHub issue, you will see that he had many suggestions, and I tried them all. And that's one, it was still 10 times slower and much lower accuracy than xgboost. So the results are here. So this have been already optimized a lot. So you can see that TabNet is running in 200 seconds, and then the best it can achieve is this 0.73 AUC. And now I trimmed already the epochs so that so the runtime originally I started with was much higher. So was minutes, and in some cases even hours. And then I just had to stop the training. And then, for example, xgboost with 200 trees, you can obtain much higher accuracy, 0.75. But if you just do 40 trees, then you obtain the same accuracy as TabNet, but more than 10 times faster. So in conclusion, I don't think that any of these specialized methods for tabular data that try to adapt deep learning so that it works well with tabular data, it's not really a success. And if we look at Kaggle surveys, at what people are using, still gradient boosting and random forest and even decision trees, they are the most used after linear and logistic regression. So from the more sophisticated methods, they are the most used, and probably because a lot of people are working with tabular data, and they simply realize that these are the best methods to use with tabular data. So ultimately, your boss, you have to please your boss. So your job is to make more money for your company, and that's gonna please your boss, and your boss doesn't care what methods you are using. If you use deep learning or gradient boosting, just use whatever is best for the use case you're using. And in this talk, I'm just talking about algorithms, like gradient boosting versus deep learning, neural nets, and different implementations. But ultimately, to have a successful machine learning project, you need to do a lot more. So what I'm talking about here is just a small piece, is maybe like 5% or 10% to the success of your whole machine learning project. So it starts with the data, then cleaning the data, exploring the data so that you understand and how to clean it. And then there is, of course, the modeling, but also the validation of the model, the deployment, and communication of the results. So there is so much more than just which algorithm you are using. So in this talk, I'm just talking about which algorithm to use, but keep in mind, this is just like a small slice of what's a successful machine learning project. So let's get into it a little bit, talk about GBMs. So GBMs are based on decision trees. Decision trees are something like represented here, where we have some data and we have an algorithm that learns a tree-like structure where there are splits based on variable values. And then at the end in the leaves, we have a prediction for classification class or for regression number. And then boosting. So the first boosting algorithm was add a boost, and then gradient boosting. They are based on training several decision trees, and then in at the end will average their prediction, and we are building this tree iteratively, and each tree is trying to correct the mistakes that were made by the ensemble of the previous trees. So that's kind of the idea. And I just put here the slides for reference and also the one with gradient boosting, but we don't need to understand the details in order for this talk. So how about what implementations to use? And a while ago, I started this benchmark. This included not only gradient boosting, but other machine learning algorithms and implementations, and it got some attention. And you can look it up on GitHub. It has this kind of scalability graphs. I was interested in how fast they're running and what accuracy they're getting and how much memory was consumed. And this was in 2015 when these things were slower and we were more restricted in memory. And at that time, the guess is that the two best implementations for gradient boosting were xgboost and H2O. And then this was 2015. And later around 2017, these other two projects were added by GBM and catboost. And all of these, they have packages readily available in R and Python, so you can just download and start using it. Very easy to use. How about Spark? So unfortunately, Spark's implementation of gradient boosting was and is still a disaster. So 100 times slower, 100 times more memory usage. So don't even waste your time trying to make it work. But you will say that, hey, but I have big data, so I need Spark. No, you probably don't have big data. Glass surveys on data science used for analytics. And also if you have big data, it's just the raw data is big, for example, clicks, but to do machine learning, you do some kind of refining and data engineering of your data into some kind of data matrix. That's probably, let's say it's prediction about users. So all those clicks are collapsed into user features, and then the data is much smaller. The data used for machine learning actually is way smaller than your original data. So it's most likely is gonna fit in the RAM of one single server. Even in 2015, you could buy 100 gigs of RAM for cheap or just rent it on the cloud. And now you have way more. And I also did a little survey of how much memory people are using for machine learning. So it's not in the size of terabytes or petabytes. And also people realize that they don't need algorithms and implementations that work on bigger data, but they just want faster. They want their machine learning to work faster. And you want faster machine learning because you train a lot of models. So if you do cross-validation, then you do more than one model. If you do hyperparameter tuning, you do lots of models. If you do ensembles, then also you train maybe hundreds of models and you ensemble them. So in a typical workflow, you will do hundreds or thousands of models. And so you cannot spend a day training one model. So that's why you want faster machine learning. So I streamlined in 2017 this benchmark repo into a new one, just focusing on the good implementation and also only on GBMs. And also I made it very reproducible. So there is like a Docker file. And I included only the best ones. So at the time it was xgboost, lightgbm, H2O, because no one is using Spark. And also I did, here's another survey where I could ask more than just the 4 options that Twitter limits you. So it's kind of the same. So people figured out which are the best implementations, and they're using mostly those. So here is 2020 catboost added to the mix. And if you look at training time, then the fastest is xgboost and lightgbm. And all of these, they have GPU implementations. So the GPU implementations, they are actually different code base than the CPU ones. So it's almost considered as a total different library. And there the xgboost one appears to be the most mature and fastest. Also, if we look at memory usage, so we can fit this data on GPU, even if it has hundreds of millions of records, because the good implementations, they use compression and various other tricks, so they fit both in traditional RAM and also on a GPU in reasonable space. However, if you want to deploy in production, then I recommend to look at H2O. So H2O is, I think, the easiest if you want to deploy as a web service. So all you need to do is this, and then you have a web service running as and you can make HTTP request as a RESTful API. So that's all you need to do, export the model and then build this. They give you they give you this tool that will build the WAR file, and then you can just run it with in Java, and then it's gonna listen on a port, and then you can just make HTTP request and get the scores. And it's very fast. It's milliseconds even for large GBMs with hundreds or thousands of trees. So a little bit about performance. I want to leave more time for questions, so I'm gonna go a little bit faster. So I looked at scalability of these libraries, depending on the number of cores you have in your CPU. And of course, it's not linear. So you would wish that jumping from 1 core to 16 cores, you would get a 16 times boost, but it's not true. And actually, a while ago was even worse. So some of these tools improved a lot over even the last 2 years. So catboost was the one that improved a lot lately, and also xgboost improved on like smaller sizes. And we also had this problem of if you had 2 or more physical CPUs in your server, then on your motherboard, then there is a bus between the 2 that's much slower than communication within the CPU.
Hi, welcome to Concord Indiana Starbucks. My name's Anna. How can I help you?
I think someone needs to mute themselves. Let's see. All right. So if you have two CPUs, actually it can create slowdowns. So you will not get speed up, you will actually run even slower than with one CPU. So my recommendation has always been to run xgboost, for example, for lightgbm on one physical CPU, and also don't use the hyper-threaded cores. I think somewhere around 16 CPU cores on one single CPU without hyper-threading is kind of the sweet spot, and apparently it's enough for most people. So if you try to use more cores, you might actually slow down your training. So you have to check for your use case. How about GPUs? So xgboost, lightgbm, the best for CPU, and xgboost the best for GPU. This is kind of what I mentioned before. And the memory usage also the best on xgboost. So usually the tool that's faster also consumes, it's just the most efficient, it consumes less memory. And for GPU implementation, there is a lot of tricks that have been used, like data compression, so that we can fit pretty big data sets even in a few gigabytes on in the GPU memory. So how many people are using GPUs? I'm not sure if I believe these surveys that I've done on Twitter. It seems like as the years pass, there is more and more people using GPUs for training gradient boosting machines. Probably the 38% is kind of too much. If you ask the same on LinkedIn, it's about half that much. So I think it's more believable. So which is the best implementation? The honest answer is it depends. And in this talk, I focus mostly on training time, but there is so much more. So if you compare implementations, there are so many other criteria you should use. So if your goal is to train fast, then xgboost or lightgbm. If you have a GPU, then xgboost. If you care about easy deployment, like really fast real-time scoring, then probably H2O. But what's for sure is that if you have tabular data, then you must try GBMs and not just go with the hype and do deep learning. All right, so I guess we'll have like 20 minutes for questions. So we're gonna go now into the Q&A, and usually when I'm running these meetups, I'm the moderator, and I ask people to ask the questions in chat, and then I'm reading them to the speaker. However, here I think it might be, I'm gonna look at the chat, but also it might be better if you guys just unmute yourself and ask the questions. So let's see how many questions are in the chat. Okay, so let's see this. Are there any cases you like random forest better than GBM? Yeah, actually, so when Kaggle started, most Kaggle competitions were won by random forest. And I think if you have like smaller data sets for tabular data, let's say around the size of 10,000 or a few 10,000s or thousands, then typically in my experience, random forest would beat gradient boosting machines because GBMs would probably overfit. But once you get like hundred thousand or hundreds of thousands of records, then GBMs start to take over. So yeah, I think if you have say 10,000 records, then you definitely want to try random forest. Yeah, also here, I agree. I think random forest is good when you don't have time to tune. Yeah, that's a good point. So I also had this kind of graph where you have on the horizontal axis effort that you put in your machine learning, and on the vertical axis, like accuracy. And of course, the more you put in, then the accuracy might increase. But yeah, there is a law of diminishing returns. So if you want something quick and you don't want to put a lot of effort into tuning, then yeah, random forest might be better. Oh yeah, good question. Have you worked on ML in financial cases? So yeah, I used to work in finance more than 20 years ago, and I'm glad I left because I had the feeling that it was very difficult to predict anything scientifically. So what I mean is that machine learning is a lot of art and not only science, but for finance, the signal to noise ratio is so low that a lot of times what your models are just random numbers. So I had the feeling that, and you know, it also depends in which areas of finance, but it's some of the use cases, I think you just came out with garbage models that weren't doing anything, but there was the pressure from your bosses or from investors to predict something, to give them something. So yes, so yeah, I remember you gave a similar talk a couple of years ago in LA, and you made some update. Yeah, that's true. So yeah, my talks kind of like have content that slowly progresses. So this added basically the TabNet and those kind of things. I don't think I've been talking about that before. Yeah, you deliberately conditioned the title on your talk on tabular data. Have you examined performance of GBMs versus deep learning on non-tabular data? Well, I don't need to. So I also mentioned in the talk that on like images, speech, and somewhat text, like deep learning is kind of the best. So I'm not contesting that at all. So there are a lot of use cases for deep learning, and where deep learning has made tremendous progress over the other methods. And yeah, if you work in those, you have those use cases, then yeah, definitely I recommend using deep learning. I don't even need to study. So we see it from Kaggle and from what's out there, that it's pretty obvious that deep learning is the best what you can have in those use cases. Although there is hype, right? So we still don't have self-driving cars. We still don't have solved a lot of these problems where some would have expected deep learning to solve them, but still compared to the other machine learning algorithms, for instance, in computer vision, yeah, deep learning is the best. This is more common than question, but I love to see you incorporate the new generation GBMs into your benchmark. Yeah, that's true. Actually, so one of the GBMs is also called, they added the name boosting into it. So somebody asked me at some point on GitHub that if I could add that library to, well, it's not really boosting. So the boosting is in the name, but actually it's a GBM. So for those of you who don't know about GBMs, so it's generalized additive models. And also there is a generalization of that. This is GBM2 by Rich Caruana. And those models are great for interpretability. And also some are claiming that they have just as good results as boosting. I'm not totally convinced on that, but you can get close performance. So, and in some use cases, it would make sense to lose a little bit of accuracy, but make sure that the model is kind of a valid one. So I recommend Rich Caruana's paper for everyone to read. It's an old paper about predicting death rate in hospitals for people with pneumonia. And the data has some flaws that if you just use the data, any machine learning algorithm will just learn the wrong thing. And then he introduces GBMs and GBMs2 as a way to figure out that something is wrong in the data and to kind of manually correct it. Oh yeah, thank you for posting the. Oh, so I assume Patrick H is Patrick Hall.
Yeah. Hey, Szilard.
Okay. All right, I got you.
Yeah, I think it's just I think EVM. So GA2M is, if it's a little bit hard to get the details. GA2M is more of like traditional statistical splines, and then they shifted to EVM, which I don't, they're kind of cagey about it, but when you pin them down, they say it's an acyclic tree boosting algorithm. I'm pretty sure it's just a GBM for each feature. And I mean, that's why they're highly accurate. It's just a really smart architecture trick. So instead of doing one big, deep or big, GBM with many trees for all your data, it's like one GBM for each feature. And then the neural network version of it is just one neural network for each feature. And I think it makes a ton of sense. And I haven't been able to take the time to see if they're really, as accurate as a traditional sort of unconstrained GBM. But I wouldn't be surprised if they were, because it's a very high capacity model, right? Like there's still a ton of rules or a ton of weights or whatever it is. And it's just a really simple architecture trick that I think the GAM architecture, like of all these different machine learning models, I think there's some chance that the GAM architecture makes the most sense for structured data. But we'll see. Yeah. I want to see it in your benchmarks, but I could help, but I don't have any time. So.
Yeah, I tried regular GAMs, not the 2, which includes pairs. So I tried it on my data for work, and it didn't perform as well as GBMs. But you have the benefit that it showed some problems with the data, which I was suspecting that it's there. It's kind of similar to the one that Rich Caruana was talking about in his pneumonia data set. So And by the way, thank you, Patrick, for hopping in. So if you don't know him, he's one of the world's best in machine learning interpretability. So whenever someone asks me about ML interpretability, I send them links to Patrick's GitHub repos.
Thank you. But yeah, that's why I like these GAM models. Yeah, because they're highly interpretable, and I mean I think they're pretty accurate. But I've seen like PyGAM do some pretty weird stuff. So you just because you use a GAM doesn't mean it's a good model or it's interpretable. It's just it can be. But yeah, my pleasure.
All right, thank you.
Going back on mute.
The question for Kukami, do you plan to rerun the benchmarks? Yes, I think I should. I haven't rerun them for about a year. So at the beginning, I used to rerun them more regularly because there were more updates and improvements in the libraries. Like, for instance, 2 years ago, xgboost multi-threading was improved a lot by some kind of very deep optimization. And also after that, catboost improved on speed. So yeah, if you guys at H2O think that you made performance improvements last year, then I should definitely rerun the benchmarks. I'm not sure, is this on the CPU or on the GPU that you guys have made changes?
On CPU.
All right, sounds good. All right, let's see. We have a couple of more minutes, so if there are some questions. Oh, I think I left this for the end. Like, I guess I'm interested in the process of the workflow start to finish. This is from Hamza. So I assume you're talking about the machine learning workflow, right? Okay.
Yeah, that's kind of what I was talking about. Is you write your code, but then how do you kind of have like a deployment or a production pipeline? What's your process, I guess, for the workflow?
Yeah, I think it kind of depends. So in a small company, it makes more sense to have like something more lean. And in a larger company where you have a larger team of data scientists, then it might make sense to have something more elaborate. There are now a lot of products, most of them commercial, that you can use. And I think larger teams, they usually they tend to use those or something like more homemade. But for like a small, very small team, I think it might make sense to just use kind of like standard tools. So you have your libraries, machine learning in either R or Python, and then you just use GitHub, and then for your code repository to keep the changes, and then also Docker to make things more reproducible and also deploy on the cloud. So, but if you have a bigger team, then you might want to look into some of the commercial products where there are also a few open source that where you can keep the results of your kind of experiments where you're trying out different hyperparameter values.
Oh, sounds good. Thank you.
All right, I guess that's pretty much. Anyone else? has maybe one more question? All right, so
No question, but I wanted to just say thanks, Szilard. It's great to hear your voice again, and nice to see where things are at for when I need to get some high performance on my tabular data.
all right, thank you, Dave. I really appreciate it.
Good talking to you.
Then let's finish here so that everyone can go do their job at the top of the hour. And thank you all for attending. I'm gonna, so this has been recorded, and I'm gonna publish the video recording. I'm not sure, is anyone who talked here or chatted, they would want to have that part cut out, or are you guys okay with publishing it? So
I'm okay.
otherwise I would not bother with cutting out parts. So I would just export the whole video and publish it. So thank you again, and see you hopefully soon, most likely in September. Sounds like a good time to continue these meetups. I already have one speaker in mind. So thank you so much for now, and see you guys in September.
Thank you.